So now we're going to address the same question we addressed in the previous video, namely the question about the existence of a bound state in an arbitrarily weak shallow potential well, but now we'll do so in more than one dimension. I should mention that there are actually very few problems in quantum mechanics in 2D and 3D which allow a relatively simple analytical solution. Most often in these cases we have to resort to either numerical analysis or rather complicated, technically complicated mathematical calculations. Well, the solution I'm going to present is not exactly trivial. It will require a lot of thinking, but otherwise it will follow almost one-to-one the steps that we used in the solution of the one-dimensional delta potential. However, very importantly, the result of these steps is going to be quite different in 2D and 3D. So namely, for those of you who want to skip the technical part and just get to the bottom lines, I will just tell you the result right away. So unlike in one dimension, where the energy of a bound state, first of all, the bound state always exists, and the energy of the bound state in the weak potential scales sort of as a power law, as a second power law of the strength of the potential. In two dimensions, it turns out that the level also always exists, but the energy of the level is extremely small. So the level is very shallow, and the energy of the level scales exponentially in a very unusual form with the strength of the potential. And this actually has very important consequences in many cases. In particular, and it relates to a certain calculation we're going to discuss in the theory of superconductivity a little later. And also, in three dimensions, it turns out that there is no level at all. So if you have a very weak attraction between particles, so for example, a very weak potential well, so this weak attraction is not going to induce a bound state, and this fact is also very important. Now let me prove the statements I just made, and the solution is going to follow very closely, as I already mentioned, the solution that we had in one dimension, which started from the Schrödinger equation for the delta potential. So now, of course, we have to deal with this Schrödinger equation in higher dimension, where wave function now is a function of a vector r, and the kinetic energy now involves this Laplacian in contrast to this derivative over x. And finally, the delta function is sort of a sharply peaked function in the d-dimensional space. So let's say in 3D, so this delta of r is simply the product of the delta function of x, delta function of y, and delta function of z. So the first step in the solution, just like in 1D, involves Fourier transforming our equation. So essentially, we go from the wave function in real space to the Fourier image of the wave function in momentum space, or more precisely here is a function of the wave vector k. So the only difference in higher dimension is that the Fourier transform is slightly more complicated, so it involves Fourier transforms along each of the directions, x, y, z, etc. So if we're in higher dimensions. And so if we perform this slightly more complicated Fourier transform, so the kinetic energy, which is basically this derivative with respect to r, becomes minus k squared. The delta function, the Fourier image of the delta function, just like in one dimension, is simply 1. And so we get to the following equation, which is just a linear equation for the Fourier image of the wave function. And as you see, there is essentially no difference between the one-dimensional case and the d-dimensional case, apart from the fact that this guy now is a vector, and while this guy was just a one-dimensional component of the wave vector. So again, we can of course solve this equation for psi tilde of k. So so we're going to have the same psi of 0 divided by h squared k squared over 2m. And I will write it as plus absolute value of the energy. Again, we're looking for a bound state, and we know that the bound state energy must be negative if it exists at all. And using exactly the same trick as before, we're going to integrate this equation, both sides of this equation, now over the entire d-dimensional space of these wave vectors. So, and if we do so, we come up with the self-consistency equation, which again in 1D and in higher dimensions look almost the same. So the only difference is that the integral here is going to over a higher dimensional space. So it turns out that this difference, the fact that we are now integrating over a higher dimensional space, leads to very important consequences for the actual solution of this equation. Here we knew that doesn't matter how small alpha is, as long as it's non-zero, we can always find an energy that would satisfy this equation. So now it turns out that for high dimension it's not going to happen necessarily. Let's say for d greater than 2 there will be no solution. So and to see this we actually have to calculate this integral that appears in the self-consistency equation that we just derived. So to do so we should first notice that the function that we're actually integrating does not depend on the directions of the wave vector. It only depends on its absolute value. So let's say in 2 dimensions we can write d2k as a dk times k, which is essentially corresponds to an integrating over the absolute value of k times d phi sub k, which is the angle that the vector k forms with the x direction. So let's say if this is our 2-dimensional k space, this would be k sub y, this would be k sub x, and so if this is our vector k, so this would be the angle phi sub k. So, and what I'm saying here is that the equation, this equation that we're looking at, so can be written as alpha d2k in this case over 2 pi squared. So this function, and we can write it as simply, well, alpha over 2 pi squared. Oops, squared is here. So dk times k over this function from 0 to infinity. So we integrate over all possible vectors, and an integral over the angles, but nothing depends on the angles. So this integral will simply give us 2 pi. So in 3D we can do the same thing. So in any dimension we can do this procedure. We can sort of integrate over the angles and just separate the integral over the magnitude of k. So let me write therefore my self-consistency equation in this form. I will write it as in any dimension. It's alpha s sub d minus 1, which I will explain what I mean by that. 2 pi to the power d. So in here I'm going to write it as dk k to the power d minus 1 h squared k squared over 2m plus absolute value of the energy. So this s sub d minus 1 is the integral that comes out of the angle. So let's say in 2 dimensions it will be simply 2 pi. Okay, so and I wrote it in this form because it actually corresponds sort of to a d minus 1 dimensional sphere. So in this case, in 2 dimensions it would be basically integrating over the circle. In 3 dimensions it would be integrating over the solid angles that cover the entire sphere. So let's say S1 is equal to 2 pi, as we just found out. So S2 is going to be equal to 4 pi. Well, we can formally introduce S0, which is just 2. Etc. So in any dimension you can in principle calculate it. So but for practical purposes we don't really need to know anything about these 3 numbers, because in real life we don't deal with anything about 3 dimensions, 2 dimensions, or 1 dimension. Now the problem, however, that appears here in already in 2 dimensions is that, well, when we integrate let's say from 0 to infinity, so the integral is actually divergent at large k. So let's say if d is equal to 2, and especially if d is equal to 3, so the higher up we go, the more divergent it becomes as we go to larger k. So this integral is actually equal to infinity. So if we look at it sort of without thinking. And well, when there is an infinity, so we have to think about why it appears. So remember that actually this constant alpha came out, well, we are solving essentially the problem for a delta potential. So our V of r is alpha times delta of r. And delta function, Dirac delta function, is a very artificial function. It was basically introduced to model a shallow potential, a physical potential that has so has a certain width. Let me call it A, and it has a certain depth, so which will be called you know, U naught. So and alpha is of the order of U naught A to the power d, where d is the dimensionality of our space. But in any case, so this delta function potential is sort of introduced to represent real physical potential that exists in reality, which has actually finite width and finite depth. So when we go to large k, large wave vectors, actually the large wave vectors correspond to small distances. And if we consider, and if we encounter a divergence at large k, which we do here, so it means that something bad happens in small distances. And so this something bad means that, well, I mean, there is no really there are no real delta potentials in nature. Okay, so all potentials have a finite radius, and so we can cut off this, in some sense, unphysical divergence by introducing a parameter 1 over a, where a is the radius of our real physical potential that we model with the delta potential. So this is actually a sort of a solution to this otherwise puzzle, because otherwise we would get infinity. We shouldn't get infinity. So basically what I'm saying here is that if we were to put a real potential in the very beginning and do everything properly, then this cutoff would appear actually naturally in our calculations. So, but here we just introduce it by hand. So now we're entering a final part of our derivation, where we will rely on the integral we just derived. So here there are no more angular components of the wave vector. There is just one integral involved, and we cut it off at 1 over a. So, and also modified it a little bit, so there is 1 over alpha. It's not a, it's alpha. It's the strength of the potential in the left hand side. So again, the main question we've been actually asking is whether there is a bound state in a weak potential. That is, in a potential where alpha goes to 0, and therefore if alpha goes to 0, 1 over alpha goes to infinity. And so the question that we're now asking is whether we can find a solution to this equation when the left-hand side is very large. So you may ask me, you just got rid of an infinity, so what are you doing? This is really would be a reasonable question, let's say, from a mathematician. But this calculation actually illustrates in a very nice way the difference between doing mathematical calculations in physics and math. So. Well, the infinity I just gotten rid of was an unphysical infinity. It's not real. It was sort of an artifact of our model. And also, this infinity was not dependent on the energy. So whether or not we put energy to 0 or to something finite, this so-called ultraviolet divergence would have existed. And so we cut it off. We sort of remembered where things came from and got rid of this divergence. Now the question is whether we can have an arbitrarily large integral by adjusting the value of the energy. Okay, and so here is basically this integral. So I don't write here this overall coefficient because it's just a number. It cannot be made large or small. It's just a number. Let's say in 2D it's 1 over 2 pi, and 3D is 1 over 2 pi squared. So it's not important. So how do we answer this question? So if we look at it, we see that the energy, absolute value of energy, appears in the denominator. Okay, so the larger the energy, the smaller this integral. It's very clear-cut tendency. So this integral is the largest when energy is equal to 0. So therefore, the question that we're really asking is whether we can, if we set this energy to 0, and the remaining integral will be k to the power d minus 1 divided by k squared, or just simply this. So the question we're asking whether the integral below can diverge. So we got rid of the divergence in the previous slide. In this slide, we're asking whether we can get it back. But the important thing here is that we want to get it back not from large momenta, but from small momenta. So the latter is called infrared divergence. Okay. And in physics, for those of you who will be thinking about becoming theoretical physicists, you may remember that infrared divergence is, if you find something like that, well, either you made a mistake, or you should, if it's new, you should think about Nobel Prize. Okay, so it's very important. Infrared divergences are real, unlike ultraviolet divergences, which are sort of artificial. So, and this boils down basically to this question. Now, clearly, if, let's say, d is equal to 3, so the dimension of space is equal to 3, the space in which we live. So then we simply have integral from 0 to 1 over a over dk is finite. There is no divergence. And therefore, the answer to the question is the question of existence of a bound state is that in 3D there is no bound state. Okay. So if alpha is sufficiently small, the right-hand side cannot possibly compete with the large value in the left-hand side. But if we go to lower dimension, and among the reasonable dimensions, 2 comes to mind. So unless we consider some fractals or whatever, so that's the only thing we can have. 1 and 2. So in 2 dimensions, this integral becomes an integral from 0 to 1 over a dk over k. And we get a very weak so-called logarithmic divergence. So at the lower limit, we're going to get 1 over 0. So and it's equal to infinity. Okay, so the integral diverges, which is great, which means that we have a bound state. So this is really the summary of what we learned from just simply considering this integral to which we simplified our problem. So if our dimensionality is smaller or equal to 2, so the integral divergence, and physically it means that there always exists a bound state. Doesn't matter how weak attraction is. So otherwise, the integral is finite and there are no bound states. So even though there is a well, there is nothing in there. There is nothing in this well. So the last thing I'm going to do is that I will estimate the value of the energy of the bound state in 2 dimensions. So we just found there is one, so let's estimate its energy. And of course, for this, I have to solve this equation specifically in 2D. So let me do so. Let me just calculate this integral, actually estimate this integral. I can, of course, calculate it exactly, but let me estimate it. It's easier. So the first thing I'm going to do, I'm going to factor out this coefficient here in front of the integral. I'm going to have m over pi h squared. And I will get an integral from 0 to 1 over a. And let me write it in this form, dk times k. And so here I'm going to have k squared plus square root of 2me over h squared. So just wrote it in this form. You will understand why. So if I set energy to 0, I have the logarithmic divergence that, well, as we know, allows the existence of the bound state. But if E is finite, so this divergence disappears, and so the smaller the E, the larger the divergence. So now, to estimate the value of the integral, I can simply move this sort of cutoff of this divergence from the denominator to the lower limit of integration. This method is called, this asymptotic method is called logarithmic accuracy. So if we have integrals of this type with logarithmic divergence, if we don't want to perform exact calculations, sometimes it's not possible. So one can just do this trick, and this provides a reasonable estimate. So if we do that, so what we're going to get is approximately, let me write it this way, approximately m over pi h squared in integral now from this 2me h squared 1 over a, and so here I will have simply dk over k, and so this of course is a logarithm, so the result is then m over pi h squared log of 1 over a, the upper limit, times h over 2me, the lower limit. And so now I'm in the position to find the energy, so I can simply solve this equation for E by exponentiating both sides of this equation, which gets rid of the logarithm. And so the result is going to be, so the energy, the absolute value of the energy is going to be, let me write, of the order of h squared over ma squared exponential of 2 pi h squared divided by alpha with a minus sign. So this is really the final result, and the result is very interesting, so for a theoretical physicist at least, because the function that we got is a very strange function. So remember that this parameter alpha controls the strength of the potential, and we consider the case when it's very small. So e to the power minus 1 over alpha is really exponentially small, very shallow level in already shallow potential well. But the function is strange because, well, if you write it e to the power minus something over alpha, so this function does not have a Taylor expansion. So remember that, you know, if we have a function f of alpha, normally at small alpha we can approximate it by f of 0 plus, you know, f prime of 0 times alpha plus f2 primes of 0 over 2 alpha squared, etc. So this is a regular Taylor expansion of a function. So in this case, all the derivatives, all the terms in this Taylor expansion are equal to 0. And this actually would have posed a problem if we had tried to solve this problem using so-called perturbation theory, which physicists love because oftentimes gives us access to solutions that are otherwise impossible to get. So we start with a known solution and then do a Taylor expansion in the vicinity of this solution. So here it wouldn't have been possible, exactly because of this weird property. So the function exists, we can plot it, we can look at it, but there is no Taylor expansion at all. It turns out that in the second lecture this week we're going to study some basics about the theory of superconductivity, and there is a classic formula in this Nobel Prize winning Bardeen-Cooper-Schrieffer theory of superconductivity, which features this function, this sort of function. Actually the reason it took people, as I will talk about it in the next lecture, the reason it took people almost 50 years to come up with a solution to the problem of superconductivity is partially because of this circumstance, that the result actually is something that can only be obtained by an exact non-perturbative calculation, but it couldn't be obtained using the perturbation theory.